So you've made the leap from the predictable world of relational databases over to Apache Spark. And you've probably hit that wall. You know the one. Your job is running super slow, or maybe it's just failing outright, and you're staring at the screen thinking, where do I even begin? Well, you're in exactly the right place. We're going to break down a really clear, repeatable way to tune and debug your Spark applications.
Here's the game plan. We'll start with how to configure things properly, to set ourselves up for success from the get-go. Then, we'll dive into the web UI for live monitoring and what to do when you have to dig into the logs. After that, we'll get into the fun stuff, the key performance levers you can pull to fix things. And finally, we'll wrap it all up into a simple workflow you can use every time.
This right here, this is the question that brings us all to the party, isn't it? Unlike a database query that just kind of runs, a Spark job has a ton of moving parts spread all across a cluster. The real secret is just knowing where to look and in what order. So let's start at the very beginning, before you even hit run.
That's right. The first step in debugging is often preventing the problem in the first place. Good configuration is everything. Think of it like telling Spark exactly what kind of resources it has to play with. Honestly, getting this part wrong is probably one of the most common reasons for bad performance right out of the gate.
So how do we give Spark its instructions? Well, there are two main ways. You can hard code some settings directly in your application with something called sparkconf. This is great for stuff that's never going to change. But for tuning, the real power, the stuff we care about, comes from using Spark submit flags when you launch the job. This lets you tweak things like memory and cores for a specific run without ever having to change a single line of your code.
Okay, so the master flag just tells Spark where to run, but these other three, these are your main tuning dials. Think of it like this. -num executors is how many workers you're hiring for the job. -executor memory is how much brain power or RAM each worker gets. And -executor cores is how many tasks each worker can juggle at the same time. Getting this trio balanced is step one.
All right, you've configured and launched your job. Now it's running, but it's crawling. It's time to switch from prevention mode to live investigation. And for that, your absolute best friend in the entire world is the Spark Web UI. It's basically your mission control, a window right into the heart of your application while it's running. You can usually find it at port 4040 on your driver machine.
Now, before we click around in the UI, we got to get the lingo down. It's pretty simple. When your code performs an action, like a count or a save, that kicks off a job. Spark breaks that job into smaller pieces called stages. Think of a stage break as a point where data has to get shuffled all around the cluster. Then, each stage is made up of a bunch of tiny tasks. The task is the smallest unit of work that actually gets sent to an executor. Understanding this helps you make sense of everything you're about to see.
The first screen you'll see is the Jobs page. This is your high-level dashboard. You can see every single action that's running, what's finished, and how long everything took. If one job is taking way longer than the others, this is your first clue. You click on that slow job to start digging deeper into its stages.
And when you click on a job, you land here, on the stage detail page. This is where the real detective work begins. You can see stats for every single task. And the number one thing you're looking for is a massive difference between the median task time and the max task time. If you see that, you found task skew. It's a classic performance killer where a few unlucky tasks got stuck with way more data to process than everybody else. The executors page gives you a bird's eye view of your workers. You can see if the work is being spread out evenly. But here's a pro tip. One of the most powerful tools in the whole UI, the thread dump. If an executor just seems stuck, you click this button and it gives you a perfect snapshot of the exact line of code it's running at that very second. It's incredible for finding things like infinite loops.
And finally, we have the storage page. If your app uses .cache or .persist to try and keep data in memory, this page is crucial. It tells you what percentage of that data actually fit. If you see a lot of data has spilled to disk, that's a huge red flag. It means you tried to cache more data than you had memory for, and Spark had to write the overflow to the much slower disk. Time to rethink your cache strategy or give your executors more memory.
Okay, but what happens when a job just dies? Or the UI shows you there's a problem, but it doesn't really tell you why it's happening? Well, that's when it's time to roll up our sleeves and head to the source of truth. The logs. These are just text files, but they contain all the juicy details, error messages, and warnings from your application.
Now, finding the right log can sometimes feel like a bit of a scavenger hunt, not gonna lie. It all depends on your cluster manager.
On a simple standalone cluster, you can just look in the work directory on your nodes. If you're using yarn, the yarn logs command is your best friend. The key, no matter what, is to scan these files for the words error or exception. That'll usually point you right to the root of the problem.
So we've played detective, we've found the clues, now it's time to switch hats and be the engineer who actually fixes the problem. There are a few main dials we can turn that can have a massive impact on performance.
The first, and maybe the most important lever, is parallelism. Spark works by splitting your data into chunks, or partitions. Each partition becomes one task. Now imagine you have a 200-core cluster, but your data is only in 20 partitions. That means 180 of your expensive cores are just sitting there, doing nothing. You're wasting almost your entire cluster. You can use repartition or coalescing in your code to make sure you have enough tasks to keep all your cores busy.
All right, you want an easy win? This is one of the easiest, most effective tuning tricks in the book. Whenever Spark sends data across the network for a shuffle, it has to serialize it. The default Java way is, well, it's slow, and it makes big objects. Just by switching to a different serializer called cryo, you can see a huge speedup. It's way faster and more compact, meaning less data has to fly across your network. It's a no-brainer.
It also really helps to understand how Spark uses the memory you give it. Think of an executor's memory like a pie. It's split into a few regions. The two big ones are for storing cached data and for shuffle operations. And you can actually control the size of those slices with a setting called spark.storage.memory_fraction. If your job does a lot of caching, you give a bigger slice to storage. If it's a shuffle-heavy job, you give a smaller slice, leaving more room for the shuffle itself.
And last but not least, don't forget the hardware itself. Spark scales beautifully, so more memory and more cores will almost always make things faster. But a really common bottleneck that people forget is the disk used for shuffling. Spark writes a ton of temporary data. If you can use multiple fast local SSDs and then tell Spark where they are with the sprq_local_dirs variable, you can dramatically speed up any job that does a lot of shuffling.
Okay, we have covered a lot of ground here, right? From configuration to monitoring to all the different levers we can pull. So let's just simplify it all and put it together into a practical workflow you can use every single time you run into a performance problem.
And this is it. This is the whole game right here. It's a loop. It's not a one-and-done fix. You start with a reasonable configuration, you run the job and monitor it to find the single biggest bottleneck. Then you apply one targeted fix, just one, and you run it again to see what happened. Then you find the next bottleneck and you repeat the whole process.
This right here is the key takeaway of this whole explainer. Performance tuning isn't some dark art where you just find one magic setting. It's a scientific process. You find the biggest problem, you apply a specific fix, and you measure the result. Then you do it again and again and again.
So, now you're a pro at making a single Spark job run as fast as humanly possible. That's awesome. But it brings up an even bigger question. In the real world, with multiple users and a budget, how do you balance raw speed with fairness and cost? How do you tune an entire cluster, not just for speed, but for maximum efficiency? Well, that sounds like a great topic for another day.
Hey, if this explainer helped demystify Spark performance tuning for you, do me a favor and hit that like button. Share it with a friend who might need it, and definitely subscribe for more deep dives just like this one. Thanks for watching.